So special relativity, we're going to start off with a little thought experiment, Max, that Albert Einstein walked through. He said, first of all, imagine we have a cannon that can launch a baseball at exactly 30 meters per second every time. So here's our cannon, and here's Sam, the target. He's holding a baseball glove, and he's standing still. What would he see if, boom, we launched the baseball at 30 meters per second? How fast would the baseball be traveling relative to Sam? This one's meant to be fairly obvious because both objects are standing still relative to each other. How fast would the baseball be traveling then? 30 meters per second. Sage, situation number 2. Same as situation number 1, but we're going to put the cannon on top of a van, and the van is traveling towards Sam at 15 meters per second. And then, boom, we fire the cannon at 30 meters per second. What would Sam see? How fast would the baseball be traveling relative to Sam? 45 meters per second. It would come scorching in. Now, the people in the van would see the baseball traveling at 30 meters per second relative to them. We're going to have to talk an awful lot, Adrian, about relative to who. What's your frame of reference? Who are you referring to? Because we are going to have multiple objects moving. So relative to the van, they would see it traveling at 30 meters per second, but Sam would see it coming in at 45 meters per second. Or, you know what? Matteo, let's redo the experiment a third time. But this time, let's have the van going away from Sam at 15 meters per second. Boom, we launch the cannon at 30 meters per second. How fast would the baseball be traveling relative to Sam? 15, Matteo, you're right. In fact, when we looked at relative velocity, I showed you the Mythbusters clip where they were driving at 60 miles an hour and they fired the soccer ball backwards at exactly 60 miles per hour, and we saw in slow motion the net velocity relative to those of us on Earth was 0. It dropped straight down. So now let's go cosmic. We have something called the Michelson-Morley experiment, probably the most famous experiment in physics because it didn't work. We say it's the most famous null result in experimental history because they were hoping to find something and they found no. In the late 19th century, 1880, 1890-ish, two physicists, Michelson and Morley, conducted an experiment. They said, you know what? That baseball analogy that I just gave you, I should be able to do that with light. So let me pause the video for a second. So just to rehash, both for the video and because you guys are teenagers, I need to repeat myself. They thought they could measure the difference in the speed of light hitting the Earth in two situations. They decided to measure the speed of light hitting the Earth when the Earth was moving towards a distant star, right here, and the speed of light hitting the Earth when the Earth was moving away from a distant star, right here. And they expected to find two slightly different answers, the same way we got the 30, or the 45 and the 15. Now, only slightly different because the speed of the Earth is so slow compared to the speed of light, but we can hopefully measure it. We'll see. So there's the picture. In January, the Earth was moving toward the star with a speed u relative to the sun. The speed of light, the symbol that we use for the speed of light always is a lowercase c. You'll see why later, but whenever you see a lowercase c in this unit, you can say, oh, speed of light. The measured speed in January was predicted to be c plus u, the speed of light plus we're moving towards it. And the measured speed in July was expected or predicted to be the speed of light minus, because we're moving away from, minus the speed of the Earth. And the speed of the Earth we can calculate pretty easily, just do observation. But the expected result didn't materialize. Instead, they got the same speed for each situation. It would be as though, in the baseball analogy that I give you, every time Sam was measuring 30 meters per second, no matter how fast the cannon was traveling. What? So here was their conclusion. Light is special. And the speed of light is a constant for all observers anywhere in the universe. The baseball analogy that I gave you will not work. Before you turn the page, what letter does the word constant begin with? C. It's why we use a C for the speed of light. It is a constant. The Michelson-Morley experiment is very famous for its negative result. In fact, Morley went to his grave believing that they had made a mistake in the experiment. He died, I think, in about 1914, and he believed, actually, no, the speed of light wasn't constant. We screwed up the measurements, and he was mortified by that. He never signed on to Einstein. But the rest of the scientists realized it showed experimentally that the speed of light is in space, in a vacuum, is the same for all observers regardless of their velocity. Regardless of whether you're traveling towards the light beam or away from the light beam, you're going to measure the same velocity for light. The speed of light, now you can turn the page if you haven't already, does not depend on your frame of reference at all. In fact, no evidence can be found that space could be used as a fixed frame of reference. Here's the short version. The speed of light is a constant. And I'll tell you how big it is. The speed of light is 3 times 10 to the 8th meters per second. It's actually 2.9996, 3. 3 times, that's a time symbol. 3 times 300 million meters per second. Okay. So, here's where Einstein came along. He knew of this result, and he said, I'm going to explain this, and here's the implication. He said, well, if speed is distance over time, or better yet, since we're going cosmic, Mateo, if speed is space over time, how can we always get the same answer for the speed of light? He said, well, that must mean that space and time change depending on the situation. So if I'm getting the same answer always on the left-hand side, then the right-hand side, there must be some weird stuff going on either in space or in time or in both. In fact, he called it space-time. Put your pencils down, look up. So where Einstein was so clever is he decided to come up with a clock because he suspected something weird was going on with time. But instead of a ticking clock, my clock will be a beam of light. See, this was very clever, Julie, because this allowed him to link light to time right away. He said, I'm going to come up with a clock where you measure how long flashes of light are apart. Flash, 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 flash. You okay with that, Adrian? So here's the experiment. Here's the thought experiment. Suppose we have a spaceship in outer space that's emitting a flash of light. We're going to use the light flash as our timer because this is going to allow us to bring the speed of light into our situation right away. Situation 1. Consider a spaceship hovering at rest. You know what? One more last time I'm going to underline the word at rest relative to the Earth. Now I had to add that phrase because, Jared, the Earth is moving through space around the sun, but let's have the spaceship moving at exactly the same rate. So relative to the Earth, the spaceship is at rest. And it's going to send a brief, regularly spaced flash of light. It's going to send a flash every 6 minutes. Every 6 minutes. Okay? Some amount of time will elapse before the flashes get to the planet. The same way it takes 8 minutes for light to reach us from the sun. So we're going to put the spaceship at just the right location. The light flashes will encounter the receiver on the planet at speed c, and the people on the Earth will see the flash every 6 minutes. Nothing spectacular here, Julie, because everything is at rest relative to each other. But since we're sending a flash out every 6 minutes, in 60 minutes, how many flashes will the ship send out? 10. And in 60 minutes, how many flashes will the Earth see? 10. Now it gets weird. You ready? Turn the page.
Wouldn't there be an extra delay on that?
Oh yeah, it would take a while for the first ones to show up, but once they saw the first one, they would see a flash every 6 minutes, is my point. Okay?
So then in 60 minutes, are you okay? Is this like starting from zero, or is this like the flash already being...
I'm saying that from the time they saw the first flash, they would see 10 flashes in 60 minutes, I believe. Okay? Here's where it gets weird, my curious friend. When speed relative or velocity relative to each other is involved, the situation is quite different. Now, it's important to note that the speed of the flashes will be constant. Try that again, Mr. Duke. Because light travels at a constant speed. This is what Einstein proposed. No matter how the ship or the receiver is moving, light is still traveling at a constant speed. However, how frequently the flashes are seen depends very much on the relative motion involved. When the ship travels toward the receiver sees the flashes more frequently. This is happening not only because time is altered due to motion, but mainly because each succeeding flash has less distance to travel because you're moving closer and closer and closer and closer and closer. So here's our picture. The spaceship is still emitting a flash every 6 minutes. But because it's moving closer to the Earth, by the time those flashes get to the Earth is going to see those flashes arriving every 3 minutes because each successive flash has less time, less distance to travel. So, as far as the spaceship is concerned, in 60 minutes, it will emit 10 flashes. And if the spaceship is using that for their clock, they will swear to you that an hour has gone by. 60 minutes. But each flash arrives at the Earth 3 minutes apart. So if the spaceship sends out 10 flashes, how long will it take for the Earth to see all 10? 30 minutes. The Earth will swear that only half an hour has gone by. And this is true. This will happen. If you were a plant on the Earth, you would have a half an hour of cell growth. If you were that same plant on the spaceship, you would experience an hour of cell growth. And you would have no way to tell the difference. Hang on. Bring the questions at the end. Okay? But I will say pause here and reflect how totally cool our universe is. You know what? Situation 3. Instead of going towards the Earth, let's go away from the Earth at the same speed, and let's still emit flashes at 6-minute intervals. However, because we're moving away from the Earth, each successive flash has further and further and further to travel, so it will take longer and longer to get to the Earth. And so we're going to pick a careful speed. Matt, we're going to pick a speed so that even though we're emitting a flash every 6 minutes, on the Earth, they're only arriving every 12 minutes. So, the effect of moving away is the opposite of moving closer to the receiver. If the flashes are received twice as frequently when the spaceship is approaching, 6-minute intervals become 3-minute intervals. They're received half as frequently when it is receiving. 2-minute flash intervals are seen every 12 minutes. So, this means that if two events are separated by 6 minutes according to the spaceship clock, they will be seen on Earth to be separated by 12 minutes when the spaceship recedes, that's the fancy word for moves away at a very high speed, and by only 3 minutes when the ship is approaching at a very high speed. This brings us to what we call the twin paradox, a dramatic illustration of time dilation. Dilation is the fancy word for lengthening or slowing down, is provided by identical twins. And this is true. This would really happen. If you had an astronaut, I'll call it twin A for astronaut, who takes a high-speed round-trip journey in the galaxy, there and back, while another twin, I'll call him twin H for stays home. When the traveling astronaut twin returns, he will be younger than his twin brother. How much younger? Depends on the relative speeds involved. You had a question.
Would it depend on the distance between the spaceship and Earth?
It gets weirder than that, and it gets weirder than that. So give me a couple of days, and I'll actually show you that space-time itself is longer or shorter, depending on what speed you're traveling at. It's even weirder than you think. But I haven't done the equations yet. So here's our summary. Suppose this spaceship emits flashes every 6 minutes during a 2-hour trip. During the first hour, it's going to go away from the Earth, which means the Earth is going to see these flashes every 12 minutes. During the second hour, first of all, it's going to turn around really quickly, and then during the second hour, it's going to return towards the Earth, but now the Earth sees the flashes every 3 minutes. Let's apply this doubling and halving of flash intervals to the twins. Suppose the traveling twin receives from the earthbound twin at the same high speed for 1 hour and then turns around and returns in 1 hour. Follow this line of reasoning. The traveling twin takes a round trip of 2 hours, according to all the clocks aboard the spaceship. However, this trip will not be seen to take 2 hours relative to the Earth. We can see this with the help of the flashes from the Earth ship's light clock. Let's fill this in together. Okay? So we have a little clock here, and the left-hand column is the ship. So the ship is going to send out a pulse every 6 minutes. In other words, in space 2, it's going to be at 12:12. Space 3, it's going to be at 12:18. Let me zoom in a little bit. Six minutes later, how much time? This is the spaceship clock. How much time? What time will it be on the spaceship? 12 what? 24. 6 minutes later, 12:30. 6 minutes later, 12:36. 6 minutes later, 12:42. 12:48. 12:54. What's 6 minutes past 12:54? Let's go 1300 instead of 1 o'clock. Sure, that works. And then moving over to the next side, 6 minutes after 1300 is going to be 1306. I know it's easy to miss one. I'm going careful here. And then 1312. 1318. 1324. 1320. Oh, not 20. 1330. 1336. 1342. 1348. 1354. 1400. This is the clock of the astronaut twin. This is the watch of the astronaut twin. When he looks at his watch, he's going to look at his watch every time he sees a flash of light, which for him is every 6 minutes. What about for the twin brother who stayed back on the Earth? Now, when we're leaving the Earth, we see the flashes 12 minutes apart when the spaceship is receding. So the astronaut is going to see the home twin, the Earth twin, is going to see the first flash at 12:12. Then 12:24. every 12 minutes. This is now relative to the Earth. The Earth sees the flashes every 12 minutes because the ship is moving further and further away, so it takes the flashes longer and longer and longer to get to the Earth. The ship sees the flashes leaving every 6 minutes, but the Earth sees them arriving every 12 minutes. In other words, we're talking about this situation right here. Top one. Is that okay? Let's keep going. So we're adding 12 now each time. 12, 36. 12, 36, and 12, 48. Here we get to 1300, yes? Here we get to 1312, 1324, 1336, 1348, 1400. Now, Julie, we're going to turn around and come back towards the Earth. When we come back towards the Earth, we noticed that this time, because we're shortening the distance every single time, Julie, the Earth sees the flashes not every 12 minutes, not every 6 minutes, but every what? 3 minutes. So now in this column over here, we were at 1400. Now it's going to be 3 minutes. 1403, 1406, 1409, 1412, 1415, 1418, 14 add 3, 21, 1424, 1427, 1430. So when these two twins meet, and twin 1 says to twin 2, what time you got? The astronaut twin is going to say 2 p.m. No. The Earth twin is going to say 2:30. The Earth twin is half an hour older. Time was different for the twin on Earth. The Earth twin aged half an hour more than the twin that went on the spaceship. What? Now, we're going to get away from doing this manually. In a little while, I'm going to show you actually Michael Einstein's equation. We're going to derive it the same way he did. But by using light as a clock, this is a natural consequence of, well, if the speed of light isn't changing, then space and time better be changing, because otherwise I can't possibly always be getting the same answer. Have I convinced you, Connor? Give me time. No pun intended. So next class, we'll see if there's a way, actually later on today, we'll see if there's a way to calculate this time change with an equation. But this leads to one question. Is it possible to travel through time? Yeah and no. Special relativity tells us that we can travel into the future, but not the past. Because the astronaut twin did travel into the future. He came back half an hour into his brother's future. Perfectly doable. Put your pencils down. Time dilation, time slowing down. What happened, along came Albert Einstein to offer the following explanation. And he began with two postulates. The first postulate, he said, if two frames of reference, two different objects, are moving with a constant velocity relative to each other, then the laws of physics will be the same in both frames. Matt, are you moving relative to me? Say no. In other words, if that means, he said, I'm going to assume that if you do an experiment and I do an experiment, we'll get the same result if we're not moving relative to each other. So I'm not going to prove that. That's just a postulate. Means you're saying, I think that's reasonable. I'm going to assume that. And I'm going to see what I can prove after that assumption. In other words, if you ever tried pouring a cup of coffee while you're on a jet plane, that's traveling 700 kilometers per hour, the coffee still pours straight down. It doesn't all end up on your lap, even though you're moving forwards, because the coffee is moving relative to you at a constant velocity, and so the laws of physics will be the same as if you were at rest. You okay with that, Kayla? Getting a little high tech here, I know. If you want to try this, try playing catch while you're inside a car, just not while you're driving. If you play catch, even though the car is moving, you'll find relative to you, the ball moves in a straight line to your partner and back, and doesn't somehow go shooting back and hit the back windshield. As long as you aren't accelerating. By the way, you don't have to, but I'm going to underline this. That got him thinking about general relativity. He started then asking himself, why does acceleration change things? Why is that so special? So, I'd like you to imagine, using your imagination, the path that this ball that's being thrown straight up and straight down in the car would take relative to an observer standing on the road looking into the van as it passes. Now, the person in the car sees the ball go straight up and straight down, but I think the person on the road would see the ball go like that because it's moving sideways at the same time as it's going up and down. You okay with that, Nick? So far, so good? Well, it turns out this was all Albert Einstein needed. This picture right here. Here is the second postulate of relativity. The second postulate of relativity says that the speed of light in space is the same for any observer, no matter what the velocity of the observer's frame of reference is. The speed of light is a constant. Constant. And this leads Albert Einstein to time dilation. Your time isn't equal to my time necessarily. Little note. Dilate means to make wider or larger, or as time gets bigger, it slows down. So according to Einstein's special theory of relativity, a clock that is moving will run slower. Michael, could you stand up, please? Could you walk across the room briskly and back? Time is traveling slower for Michael right now than for us. His body is aging slower. The atoms in his body are decaying slower. Time slowed down for him relative to us. Now, your speed compared to the speed of light is so minuscule that really the effect is negligible, but we'll start to calculate when it does make a difference. This stretching of time is called time dilation. And I told you one of Albert Einstein's very clever ideas was to say, I'm going to build my clock out of a beam of light. I'm not going to have a ticking pendulum clock or a clock that ticks. I'm going to bounce a beam of light back and forth at regular intervals because it seems to me that that's the same as a clock. But that lets me bring light into my situation right away. So here was what he imagined. He imagined a spaceship, and he imagined a mirror with a beam of light bouncing off the mirror, going up and then down. The spaceship is traveling at a speed v, and then we're going to take it from there. So is it possible that in 2 frames of reference, identical clocks might run differently and that time might pass differently? Yes! This is one of the predictions of Albert Einstein's special theory. Special theory of relativity, he showed that moving objects relative to each other cause time to slow down. In general relativity, he showed that gravitational fields also cause time to slow down. So before you guys can turn the page, but figure 15.6 illustrates an observer inside an imaginary custom-made glass-walled spaceship. Why glass walls? So that we can see inside. The inside observer is watching an event consisting of an imaginary oscillating light beam going beep, 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 beep. Now, in real life, it would be happening crazy fast, but let's imagine that we could see it, that we could process that fast. The oscillating light beam acts like a clock. The beam goes from the source up to mirror A and back. So the inside observer measures the time for the light to travel from A to B, and he finds that that time is t0. I'm going to go algebraic. I don't want to use numbers. Oh, and since distance equals speed times time, the distance is the speed of light times t0. That's the distance the inside observer sees the beam of light travel. In other words, this distance here is c times t0. You okay with that? Now what about the observer on the outside looking through the wall? Well, the observer sees a different distance and a different time. I'm going to call that time t. And this distance is going to be, he still measures the same speed of light, or she still measures the same speed of light, times t. So this distance is c times t. This distance is c times t0. And then this distance here is the speed of the ship times time. Which time? What the observer sees. So my argument right now is, Max, I got a distance, I got a distance, I got a distance. Not only that, I have a triangle. What I love about Albert Einstein was he proved special relativity using Pythagoras, Math 8. See the right angle triangle there? We're going to write an equation. And our equation is going to look like this. Dolp, draw a little picture. So the triangle that we're talking about has this distance as c times the time that the observer sees. Sorry, the time that the spaceship, the person inside the spaceship sees. The hypotenuse is c times the time that the person outside the spaceship sees. And the distance the spaceship travels forward is the speed of the spaceship times the time that the outside observer sees. Pythagoras says this: a squared plus b squared equals c squared. I'm going to walk you through, Sage, the derivation. I'm not going to make you recreate this. I'm going to ask you to use the equations that we get at the end. So you ready? Put your thinking cap on. It's going to be this: c times t0 squared. There's a. See it? Plus, what's b? What side is side little b in Pythagoras? VT all squared equals CT all squared. Then Einstein got this thing, the CT0 squared by itself, so I need to move this over. How would I move this over? What's right in front of it? So how will I move it over? So he said, okay, my next line is going to look like this. CT0 squared equals CT squared minus VT squared. You okay with that? Then he decided to distribute the powers. So he went, okay, that squared goes on to there and on to there. That squared goes on to there and on to there. That squared goes on to there and on to there. He got rid of the brackets, in other words. He said, okay, now it's going to be c squared t0 squared equals c squared t squared minus v squared t squared. Then, Karn, is there a t squared right there? Say yes. Is there a t squared right there? He said, that's a GCF. That's the greatest common factor. I'm going to factor it out. Now, by the way, so far we used Math 8 and Math 9 to prove one of the most important laws of physics. So this is kind of nerdily cool. So we're going to factor it out. It's going to look like this. The c squared t 0 squared drops down. When I factor out a t squared in brackets, I have c squared minus v squared. Okay. Then he said, I want to get this by itself, the t0. What's in front of the t0? A c squared. What's the c squared doing to the t0? So how will he move it over? Oh boy, this formula manipulation junk again. Yeah. So he said, okay, I get this. t0 squared equals, and he said, instead of dividing the front part, I'm going to put the c squared here. He said, I'll just divide everything in the bracket. That's the same as dividing the front. Why did he do that? Right here. What does that simplify to? 1. Oh, a little nicer. A little nicer. So he said, okay, this can now be written as t0 squared equals t squared bracket 1 minus v squared over c squared. Final step, what do I want to get by itself? The t. Oh, see, there's a t squared. There's this bracket. How could I move this bracket over? Okay, so he went... Except he said, I want to get the t by itself. I've got the t squared by itself. How to get rid of a squared? This final step, he went like that. He took the square root of the top. Oh, look up. Wait a minute. He said, if I take the square root of the top, that squared is just going to vanish. But I'll put the bottom inside a square root. This is Einstein's time dilation equation. It says this. Time equals t0 all over the square root of 1 minus v squared over c squared. This is on your yellow formula sheet on the back page. Where t equals the dilated time, t0 equals the time for the moving object, the spaceship, v equals the speed of the moving object, and c equals speed of light. We're going to do one, get your calculators out, and then we're going to press pause. Going to come back to example 1 for a second. Let's go to example 2. A spaceship is traveling at 85% the speed of light. If 1 year passes on the spaceship, how much time passes back on Earth? Let's go back to our DFIC approach because this is brand new. What's this question asking me to find? Time? Which one? T or T0? T. So I'm going to go like this. Is that okay, Ty? All right. What's T0? How much time passes on the spaceship?
1 year.
Oh, I like that. By the way, you don't have to change it to seconds. If you put in years, you'll get years as an answer. If you put in hours, you'll get hours as an answer. So just whatever time unit you put in, that's what you get out. What's the speed? Well, it's going to be 85% of the speed of light. Now, how do we write that? First of all, I don't do math with a percent. I change it to a decimal. What is 85% as a decimal?
0.5.
What would 85% of the speed of light be? It would be this, 0.85 times c, because that's how you'd find the percentage. Don't bother doing the math. Just write it like that. I'm not going to bother calculating it. You'll see why in a second. Here's our equation. T equals T0 all over the square root of 1 minus v squared over c squared. I went from memory, is that correct? You guys have it in the box up there?
Yeah.
Okay. What's T0? How much time passes on the spaceship? 1 year. Divided by the square root of 1 minus. This is why I didn't bother calculating the v. Here's what I'm going to get. 0.85c over c all squared. Is that okay, Jared? Because if you're squaring the top and the bottom, it's the same as squaring the whole thing. Why did I write it that way? Is there a c on the top? In the mini fraction, is there a c on the top? Is there a c on the bottom? So what if I give you the speed as a percentage of the speed of light? Conveniently in this equation, that will always happen if you just put it in as a decimal. All right. So here's what I really have. 1 over the square root of 1 minus 0.85 squared. Get your calculators out, and I'd like to give you some advice on how I type these in. Got your calculator out? Mateo, got your calculator out? I tend to do what's inside the square root first. I'm going to go like this. 1 minus 0.85 squared equals. That's what's inside the square root. Now I take the square root of that. Square root answer button. The bottom works out to that. Did I say bottom? The final answer is going to be 1 divided by that. $1.9 years. Almost 2 years. This person traveling for 1 year, their watch and their calendar, they would measure 1 year. They would age for 1 year. When they came back, they would find everybody back on Earth had aged 1.9 years. And that's been measured with the jet plane experiment that we did in the 70s. Now, we can't, at this current level of our technology, get large objects up to 85% the speed of light. But small objects, like particles, we can. So that's what the colliders do. Okay? So we're going to go like this.